Before there were stars, before there was light, before there was even time itself, there was no space to move through and no moment for anything to happen. And yet somehow, from that absolute silence, everything we have ever known began to exist. The beginning of everything is not a single explosion happening in one place, but a slow unfolding of reality itself, where space stretches, time starts ticking, and the laws of physics quietly switch on, shaping a universe that would take billions of years to become recognizable. When we talk about the beginning, we are not talking about a moment we could stand next to or watch from a distance, because there was no next to, no outside, and no before in the way we usually imagine it. There was only the first emergence of space and time together, woven into a single fabric that would eventually hold galaxies, stars, planets, and life itself. In this video, we will gently explore 101 carefully chosen facts about how everything began, from the earliest fractions of a second after time was born, to the quiet processes that allowed matter to form, light to travel, and structure to slowly appear in a universe that started out smooth, hot, and nearly identical everywhere. Each fact is meant to be taken slowly, allowing your mind to drift while still following the story of existence itself, because the beginning of everything is not just a scientific question, but a deeply human one, touching on where we come from and why there is something rather than nothing at all. If you enjoy calm explanations that help you relax while learning about the universe, consider subscribing to Theories Before Sleep, where we explore the deepest questions of reality, gently and without rush. Now, let's begin our journey back to the very first moments, where time itself takes its first breath, and the story of everything quietly starts. When we talk about the beginning of everything, it is tempting to imagine a dramatic event, a sudden explosion happening at a specific point in space, like a firework igniting in an already existing darkness. But this image is misleading, because at the beginning, there was no space for anything to explode into, and no time in which the explosion could occur. The beginning of everything is not an event inside the universe. It is the beginning of the universe itself, meaning that space and time do not exist before this moment, and therefore cannot surround it or contain it in any familiar way. This makes the origin of everything difficult to picture, because our minds are built to understand causes happening before effects, moments following other moments, and objects existing somewhere. But the beginning of the universe does not fit into these categories. At the very beginning, time itself begins, which means there is no meaningful sense in which something happens before the universe starts, because before is a concept that only makes sense once time already exists. This is why physicists often say that asking what happened before the Big Bang may be similar to asking what lies north of the North Pole, because the question assumes a direction or dimension that stops existing at that boundary. In the earliest description we have, the universe begins in an extremely hot, extremely dense state, where all of space is compressed and energy dominates everything, not located at a single point, but present everywhere at once. This early universe is not empty and then filled, it is already full from the very beginning, filled with energy and potential, expanding as time begins to flow. As space expands, it carries matter and energy with it, meaning galaxies are not flying away from a central explosion, but are instead being carried apart by the stretching of space itself. In these first moments, the laws of physics as we know them are present, but they operate under conditions so extreme that many of our current theories stop working cleanly, forcing physicists to rely on approximations and mathematical extrapolations. Temperatures are so high that particles cannot form stable structures, and energy constantly transforms into matter and back again, creating a seething cosmic soup where nothing familiar can survive. At this stage, there are no atoms, no nuclei, no protons or neutrons as we know them, only fundamental fields and particles interacting in ways that are still not fully understood. The universe at this point is nearly perfectly uniform, meaning it looks almost the same everywhere, with only tiny fluctuations in density that will later grow into galaxies and large-scale structure. These tiny irregularities are crucial, because without them, gravity would have nothing to amplify, and the universe would remain forever smooth and featureless. As the universe expands, it also cools, and cooling allows new forms of matter to become stable, much like steam condensing into water as temperature drops. Within fractions of a second, forces that were once unified begin to separate, gravity becoming distinct from the other fundamental interactions, followed later by the separation of electromagnetic and nuclear forces. This separation of forces sets the stage for all future complexity, determining how particles interact, how atoms form, and how stars and galaxies will eventually come into existence. One of the most remarkable aspects of the beginning is how precisely balanced the universe appears to be, with conditions that allow expansion to continue at just the right rate for structure to form, rather than collapsing back in on itself or expanding too quickly for matter to clump together. Small changes in the early conditions could have resulted in a universe with no stars, no galaxies, and no possibility for life. Yet the universe we inhabit seems delicately poised between these extremes. As time progresses from its first instance, the universe transitions from a state dominated by radiation to one where matter begins to play a larger role, allowing gravity to slowly sculpt the cosmos. Quarks combine to form protons and neutrons, which later join to create the nuclei of the lightest elements, mainly hydrogen and helium, in a process known as primordial nucleosynthesis. This early creation of elements sets the chemical foundation of the universe, determining what kinds of matter will be available for future stars and galaxies. For hundreds of thousands of years, the universe remains hot enough that electrons cannot bind to nuclei, leaving space filled with a glowing plasma that scatters light in all directions. Eventually, as expansion continues and temperatures fall further, electrons finally attach to nuclei, forming the first neutral atoms and allowing light to travel freely for the first time. The faint afterglow of this moment still fills the universe today as the cosmic microwave background, a silent echo of the universe's early history stretched thin by billions of years of expansion. This background radiation provides one of the strongest pieces of evidence for the Big Bang, offering a snapshot of the universe when it was young, smooth, and only beginning to develop structure. From this point onward, the universe enters a long, slow process of change, driven primarily by gravity, as tiny differences in density gradually grow larger over immense spans of time. regions slightly denser than average attract more matter, becoming seeds for future galaxies, while less dense regions become vast cosmic voids. Over hundreds of millions of years, the first stars ignite, transforming simple hydrogen and helium into heavier elements and beginning the long chain of cosmic evolution that eventually leads to planets, chemistry, and life. But all of this complexity traces back to those first moments, when the universe was simple, hot, and nearly uniform, governed by laws that were just beginning to express themselves. The beginning of everything is therefore not a single dramatic flash, but a gradual unfolding of structure from simplicity, guided by expansion, cooling, and the quiet persistence of physical law. Even now, as the universe continues to expand, the imprint of its beginning remains visible in the large-scale structure of galaxies and in the background radiation that fills all of space. Understanding the beginning of everything is not just about looking backward in time, but about recognizing how deeply the past is woven into the present, shaping the universe we see today. And this is only the first step in a much longer journey, because the beginning does not end with the formation of matter, but continues through inflation, structure, and the slow emergence of complexity that defines our cosmic story. In the earliest moments after the beginning, the universe did not simply expand in a calm and steady way, but entered a phase of extraordinary growth that reshaped everything that would come after, a period known as cosmic inflation, where space itself expanded at a rate far beyond anything we observe today. Inflation is not about matter flying outward, or energy exploding into emptiness, but about the fabric of space stretching so rapidly that distances between points increased faster than light could travel between them, not violating physics, but revealing how different expansion is from motion through space. During this brief but powerful phase, regions of the universe that were once unimaginably close were suddenly separated by enormous distances, smoothing out irregularities and explaining why the universe appears nearly uniform in every direction we look. This rapid expansion helps explain one of the deepest puzzles in cosmology: why distant regions of the universe that have never had time to communicate with each other still share almost the same temperature and physical properties. Inflation acts like a cosmic reset, stretching space so efficiently that any initial curvature or irregular structure becomes nearly invisible, leaving behind a universe that appears flat and balanced on the larger scales. At the same time, inflation does not erase everything, because tiny quantum fluctuations that existed at the smallest scales are also stretched, becoming the seeds of all future structure. These fluctuations are not imperfections in the process, but essential features, because they introduce the slight variations in density that gravity later amplifies into galaxies, stars, and cosmic filaments. In this way, the largest structures in the universe today trace their origins back to the smallest quantum processes imaginable, linking the physics of the very small with the architecture of the cosmos itself. As inflation ends, the energy driving this rapid expansion transforms into particles and radiation, filling the universe with a hot, dense mixture that marks the beginning of the more familiar Big Bang expansion. From this point onward, the universe continues to expand, but at a much slower and more predictable rate, allowing time for particles to interact, forces to operate distinctly, and matter to gradually organize. The end of inflation does not mark a clean boundary, but a transition from a universe dominated by a mysterious energy field to one governed by radiation and matter. In the moments following this transition, the universe is still unimaginably hot, dense, and energetic, but it now evolves in a way that can be described by well-tested physical theories. As expansion continues, the universe cools, allowing particles to exist in stable forms and interact according to the fundamental forces that have now separated into their familiar roles. This cooling process is slow and relentless, driven by the expansion of space itself, which spreads energy over ever larger volumes. The universe at this stage resembles a vast glowing plasma filled with charged particles that constantly collide and scatter light, preventing photons from travelling freely. Despite this apparent chaos, the universe remains remarkably uniform on large scales, with only tiny variations that carry the imprint of inflation's quantum origins. These variations are measured today in the cosmic microwave background, providing strong evidence that inflation occurred and that the early universe behaved in a highly specific way. One of the most profound implications of inflation is that it suggests our observable universe may be only a small part of a much larger reality, possibly one of many regions that underwent similar expansion. In some theories, inflation never fully ends everywhere, leading to a scenario where new regions of space continue to inflate, forming a vast multiverse with diverse physical properties. While these ideas remain speculative, they highlight how the beginning of everything may be more complex and expansive than a single event confined to one universe. As the universe exits inflation and enters a more stable expansion, the balance between gravity and expansion becomes crucial, determining whether matter can clump together or be pulled apart too quickly. In our universe, this balance allows gravity to slowly gather matter, forming the first dense regions that will eventually ignite into stars. However, this process takes time, and for hundreds of thousands of years, the universe remains dark in the sense that light cannot yet travel freely across space. This early darkness is not emptiness but opacity, a universe filled with energy and matter that has not yet settled into the structures we recognize. During this period, the universe is governed by simple rules, expanding, cooling, and evolving predictably, yet laying the groundwork for extraordinary complexity. The precise nature of inflation remains one of the greatest open questions in physics, with scientists seeking evidence that can reveal what drove it and how it began. Despite these uncertainties, inflation provides a powerful framework for understanding why the universe looks the way it does on the largest scales. It explains why space appears flat, why distant regions look similar, and why small variations exist that lead to structure rather than uniform emptiness. The beginning of everything is therefore not only about the birth of space and time, but about a delicate choreography between expansion and fluctuation, simplicity and potential. Inflation transforms a universe that could have been chaotic and unpredictable into one that is smooth, balanced, and capable of supporting complexity. Even now, billions of years later, the fingerprints of this earliest expansion remain visible in the structure of galaxies and the faint radiation that fills space. By studying these traces, we are not just learning about the past, but uncovering the rules that govern how reality itself unfolds. The universe's rapid early growth sets the stage for everything that follows, from the formation of atoms to the emergence of stars, planets, and life. And yet, despite its importance, inflation is only one chapter in the beginning of everything. Brief but transformative phase that opens the door to the slow, patient evolution of the cosmos. After inflation ended and the universe settled into a calmer expansion, the next great transformation was not dramatic in appearance, but foundational in consequence, because it was during this long, early era that matter learned how to exist in stable forms rather than flashing briefly in and out of existence. As the universe continued to expand and cool, energy no longer dominated every interaction, and conditions slowly became favourable for particles to remain bound together rather than instantly dissolving back into radiation. In the first moments after inflation, matter and antimatter were created in nearly equal amounts, forming pairs that annihilated one another whenever they met, releasing energy back into the universe. For reasons that are still not fully understood, a tiny imbalance existed between matter and antimatter, leaving just a slight excess of matter after most annihilations had occurred. This small difference was enough to shape the entire future of the universe, because without it, no matter would have survived, and the cosmos would consist only of radiation expanding forever. As temperatures dropped further, quarks began to bind together, forming protons and neutrons, the building blocks of atomic nuclei, in a process governed by the strong nuclear force. These protons and neutrons did not immediately form complex structures, but instead existed in a dense, hot environment where collisions were frequent and energies remained high. Within the first few minutes after the beginning, the universe entered a phase known as primordial nucleosynthesis, during which the lightest atomic nuclei began to form. Protons and neutrons combined to create nuclei of hydrogen, helium, and trace amounts of lithium, setting the initial chemical composition of the universe. This early nuclear synthesis was brief, because as the universe continued to expand and cool, conditions quickly became too cold and diffuse for nuclear reactions to proceed efficiently. As a result, the universe emerged from this phase with a remarkably simple composition, dominated by hydrogen and helium, elements that would later fuel the formation of stars. For a long time afterward, the universe remained in a state where matter existed mostly as free nuclei and electrons, forming a hot ionized plasma that filled all of space. Photons constantly scattered off these charged particles, meaning light could not travel freely, and the universe remained opaque despite being filled with intense radiation. This period is sometimes described as a cosmic fog, not because space was empty, but because light itself was trapped in constant interaction with matter. As expansion continued, temperatures dropped to a point where electrons could finally bind to nuclei without being immediately knocked free by energetic collisions. This moment, known as recombination, marked the formation of the first neutral atoms, allowing the universe to become transparent for the first time. Once electrons settled into stable orbits around nuclei, photons were no longer constantly scattered, and light began to travel freely across space. The radiation released at this moment continues to fill the universe today as the cosmic microwave background, stretched and cooled by billions of years of expansion. This background radiation is not just a relic of the past, but a detailed record of the universe at a time when matter had just begun to exist in stable forms. Tiny variations in temperature within this radiation reflect the density fluctuations that were imprinted during inflation and later amplified by gravity. After recombination, the universe entered a long period sometimes called the Cosmic Dark Ages, not because nothing existed, but because there were no stars or galaxies to produce visible light. During this time, matter continued to respond to gravity, slowly gathering into denser regions where future structures would form. Hydrogen and helium gas accumulated within slight gravitational wells, gradually becoming more concentrated as expansion slowed their separation. This process was slow and patient, unfolding over hundreds of millions of years, guided by gravity acting on the initial irregularities seeded in the earliest moments. As gas clouds grew denser, their internal temperatures rose, eventually reaching conditions where nuclear fusion could ignite. The first stars formed not long after, ending the Dark Ages and transforming the universe by producing light and heavier elements for the first time. These early stars were massive and short-lived, burning intensely and exploding as supernovae, enriching their surroundings with heavier elements forged in their cores. This enrichment allowed later generations of stars to form planets, complex chemistry, and eventually environments capable of supporting life. But none of this would have been possible without the earlier stages where matter learned how to stay together long enough to form stable structures. The emergence of matter was not inevitable, but the result of a delicate balance between expansion, cooling, and the fundamental forces governing interaction. Too rapid an expansion, and matter would never clump. Too slow, and the universe could collapse back on itself before complexity had a chance to emerge. Instead, the universe followed a narrow path where simplicity gradually gave way to structure and uniformity gave way to diversity. The beginning of everything is therefore not just about the birth of space and time, but about the gradual emergence of persistence, where particles remain, atoms form, and matter begins to endure. This endurance allows the universe to develop memory in a physical sense, preserving information in structures that can influence future evolution. Each stage builds upon the previous one, creating a chain of dependency that links the earliest moments to the present cosmos. By understanding how matter emerged and stabilized, we gain insight into why the universe looks the way it does, and why it is capable of supporting complexity at all. After matter learned how to remain stable and light was finally free to travel through space, the universe entered a long and quiet phase where its future shape was determined not by sudden events, but by the steady and patient pull of gravity acting over immense stretches of time. Gravity does not announce itself with noise or light, and it does not rush, but from the very beginning it has been the force that quietly organizes matter, drawing particles together, shaping structure, and turning tiny differences into vast cosmic forms. In the early universe, after recombination, matter was spread almost evenly across space, with only slight variations in density left behind from inflation, differences so small they would be nearly invisible if not for gravity's amplifying effect. Where matter was just a little denser than average, gravity exerted a slightly stronger pull, attracting more material and deepening these regions over time, while less dense regions gradually emptied out. This process did not happen quickly, and for millions of years the universe looked nearly the same everywhere, filled with diffuse clouds of hydrogen and helium drifting slowly through expanding space. But gravity is relentless, and even the smallest imbalance, given enough time, grows into something significant, shaping the universe not through forceful intervention, but through persistence. One of the most important players in this stage of cosmic evolution is dark matter, a form of matter that does not emit, absorb, or reflect light, making it invisible to direct observation, yet dominant in its gravitational influence. Dark matter began to clump earlier than ordinary matter because it did not interact with radiation in the same way, allowing it to start forming structures even before atoms existed. These early dark matter clumps acted like invisible scaffolding, guiding ordinary matter into growing concentrations where galaxies would eventually form. As hydrogen and helium gas fell into these gravitational wells, it became denser and warmer, slowly approaching the conditions needed to ignite the first stars. This infall was not smooth or symmetrical, but chaotic and uneven, leading to complex flows of gas that set the stage for the rich variety of structures seen in the universe today. Over time, these dense regions grew into the first protogalaxies, loose and irregular collections of gas and dark matter that would later evolve into more familiar shapes. The universe at this stage was still mostly dark, illuminated only by the faint afterglow of the cosmic microwave background, but change was quietly underway. As gas continued to accumulate, gravity compressed it further, raising temperatures and pressures until nuclear fusion could begin in the cores of the first stars. These first stars marked a turning point in cosmic history, because for the first time since recombination, the universe produced its own light sources rather than relying on leftover radiation from the beginning. The light from these early stars began to ionize the surrounding hydrogen, slowly transforming the universe from a neutral state back into an ionized one in a process known as reionization. This transformation did not occur everywhere at once, but spread outward from regions of star formation, creating bubbles of ionized gas that gradually grew and overlapped. As more stars formed, these bubbles expanded until nearly all of the hydrogen in the universe became ionized again, allowing light to travel freely over vast distances. The formation of stars also initiated the production of heavier elements, because fusion inside stellar cores creates atoms heavier than hydrogen and helium. When massive stars ended their lives in supernova explosions, they scattered these newly formed elements into surrounding space, enriching the cosmic environment. This enrichment allowed later generations of stars to form planets and more complex chemical systems, linking gravity's early work to the eventual emergence of life. Galaxies continued to grow by attracting more matter and by merging with other galaxies, a process that remains ongoing even today. These mergers were not violent in the way collisions are on smaller scales, because the vast distances between stars mean direct impacts are rare, but they dramatically reshaped galaxies over time. Some galaxies developed elegant spiral arms, others became smooth ellipticals, and many retained irregular forms, reflecting the diverse paths taken during their formation. On the larger scales, gravity organized galaxies into clusters and superclusters, connected by long filaments of matter and separated by enormous voids. This cosmic web structure is one of the most striking features of the universe, revealing how gravity shapes matter into patterns that span hundreds of millions of light years. The web-like arrangement traces the underlying distribution of dark matter, making visible the invisible framework that governs cosmic structure. As the universe continued to expand, the balance between gravity and expansion became increasingly important, determining how easily structures could grow. In regions where gravity was strong enough, matter continued to clump, while in others, expansion pulled material apart faster than it could collapse. This competition between gravity and expansion continues to shape the universe today, influencing the formation of new stars and galaxies. Over billions of years, gravity transformed a nearly uniform universe into one filled with structure, contrast, and complexity, all arising from tiny differences present at the beginning. The process did not require direction or purpose, only the consistent application of physical law over time. Every galaxy, every star, and every planet exists because gravity patiently amplified small irregularities into enduring forms, evened. Now, gravity continues its work, drawing galaxies together, bending light, and shaping the flow of matter across space. The universe's large-scale structure is therefore not a static arrangement, but a living record of gravity's influence across cosmic time. By studying these structures, we gain insight into the conditions of the early universe and the forces that guided its evolution. The beginning of everything is written into the distribution of galaxies and the patterns of matter we observe today. As gravity continued to draw matter together into stars, galaxies, and vast cosmic structures, another quieter transformation was unfolding at the largest scales, one that would slowly change the fate of the universe itself. The discovery that expansion was not slowing down as expected, but accelerating. For much of cosmic history, gravity appeared to dominate the story, pulling matter inward, shaping galaxies and resisting the outward stretch of space, leading scientists to expect that expansion might eventually slow or even reverse. Instead, careful observations revealed something unexpected, that distant galaxies were not just moving away from us, but doing so at an increasing rate, as if space itself were being pushed apart by an unseen influence. This acceleration is attributed to what we now call dark energy, a mysterious component of the universe that does not clump like matter and does not shine like stars, but exerts a gentle, persistent pressure on the fabric of space itself. Dark energy does not act locally, and it does not gather into structures, but instead appears to be a property of space as a whole, becoming more influential as the universe expands and matter becomes more diluted. In the early universe, when matter was dense and closely packed, gravity dominated the dynamics of expansion, but as space grew larger and matter spread thinner, dark energy gradually took over. This shift marks a new era in cosmic history, where the large-scale evolution of the universe is guided not by attraction, but by a subtle form of repulsion embedded in space itself. The effect of dark energy is not dramatic or explosive, but cumulative, gently increasing the rate at which galaxies drift apart over billions of years. On small scales, such as within galaxies or clusters, gravity remains strong enough to hold structures together, meaning stars continue to orbit, galaxies continue to merge and local systems remain stable. But on the larger scales, beyond the reach of gravity's binding power, expansion accelerates, gradually isolating regions of the universe from one another. As time passes, distant galaxies move beyond our observable horizon, their light stretched and dimmed until it can no longer reach us, effectively disappearing from view. This process does not remove galaxies from existence, but removes them from causal contact, meaning their future and ours can no longer influence each other. The universe becomes increasingly fragmented into isolated islands of matter, each surrounded by expanding space that grows faster than any signal can cross. Over immense timescales, this leads to a universe where each galaxy cluster exists in near complete isolation, with the rest of the cosmos fading into darkness. This accelerating expansion also affects the long-term formation of structure, because as space expands faster, it becomes harder for gravity to draw new matter together. Eventually, the era of galaxy formation slows and then ends, not because matter disappears, but because expansion prevents new structures from forming across large distances. Stars continue to form within existing galaxies for billions of years, but even this process is finite, as the raw material needed for star formation is gradually used up or dispersed. As star formation declines, galaxies grow dimmer, transitioning from vibrant systems filled with young stars to quieter collections of older, cooler ones. The universe does not suddenly change its appearance, but slowly shifts toward a darker and more diffuse state, guided by expansion and the steady influence of dark energy. This future is not catastrophic, but gradual, unfolding so slowly that no single moment marks the transition from one era to the next. The acceleration of expansion also reshapes our understanding of the beginning, because it suggests that the universe's fate is closely linked to the same fundamental properties of space that governed its earliest moments. Just as inflation drove an early period of rapid expansion, dark energy drives a late-time acceleration, hinting at deep connections between the universe's birth and its long-term evolution. Whether dark energy remains constant, grows stronger, or changes over time remains one of the greatest unanswered questions in cosmology. Different possibilities lead to vastly different futures, from endless expansion to dramatic scenarios where structure is torn apart. What remains clear is that expansion is not simply a passive backdrop, but an active player in the universe's story, shaping what can form, what can endure, and what will eventually fade away. The same expansion that allowed the universe to cool and form matter now acts to separate and isolate, demonstrating how physical processes can have different consequences at different stages of cosmic history. The universe does not evolve toward a goal, but follows the implications of its fundamental properties wherever they lead. Acceleration does not undo the work of gravity, but limits its reach, drawing a boundary between what can remain connected and what must drift apart. Over time, this boundary moves closer, shrinking the portion of the universe that any observer can access or influence. The beginning of everything therefore contains within it the seeds not only of structure and complexity, but also of separation and isolation. The same laws that made galaxies possible also ensure that, eventually, those galaxies will become increasingly alone. This realization does not diminish the significance of the universe's early history, but deepens it, revealing a cosmos shaped by balance, transition, and change at every scale. As the universe continues to expand and drift apart on its largest scales, the smaller, brighter actors of the cosmos follow their own quieter timelines, because stars, unlike space itself, are finite, burning steadily through their fuel as time passes, whether expansion accelerates or not. Stars are not eternal lights fixed into the sky, but temporary balances between gravity pulling inward and nuclear fusion pushing outward, a balance that lasts only as long as fuel remains in their cores. From the moment a star ignites, it begins a slow countdown, converting hydrogen into helium, releasing energy that shines across space and warms planets that may orbit nearby. For smaller stars, this process unfolds slowly and patiently, allowing them to shine for tens or even hundreds of billions of years, far longer than the universe has existed so far. Larger stars live much faster lives, burning through their fuel at a furious pace, shining brilliantly for only a few million years before exhausting the resources that keep them stable. When a star's core runs low on usable fuel, the balance that held it together begins to shift, and gravity slowly gains the upper hand. In smaller stars, this leads to a gentle fading, as fusion slows and the star cools, eventually leaving behind a dense remnant known as a white dwarf. These white dwarfs no longer produce energy through fusion, but glow faintly from leftover heat, slowly cooling over trillions of years in the darkness of space. Larger stars meet more dramatic ends, expanding into red giants before collapsing and exploding as supernovae, scattering heavy elements into surrounding space. These explosions are not just endings, but acts of creation, forging and distributing elements like carbon, oxygen, and iron, materials essential for planets and life. Over cosmic time, repeated cycles of star birth and death enrich galaxies, allowing each new generation of stars to form from more complex material than the last. But this process cannot continue forever, because star formation depends on cold gas, and that gas is gradually consumed or dispersed as stars form and die. As expansion accelerates and galaxies become more isolated, fresh material becomes harder to gather, and the rate of star formation steadily declines. Eventually, galaxies enter an era where few new stars are born and existing stars age without replacement, slowly dimming the universe. In this future, galaxies that once blazed with light become quieter and darker, populated mainly by long-lived, low-mass stars and stellar remnants. The universe does not suddenly go dark, but fades gradually, as fewer bright stars remain to illuminate space. Over unimaginably long timescales, even the longest-lived stars exhaust their fuel, leaving behind a universe dominated by stellar remnants. White dwarfs, neutron stars, and black holes become the most common outcomes of stellar evolution, each carrying the mass of former stars without their light. Neutron stars, incredibly dense objects formed from the collapsed cores of massive stars, slowly lose energy over time, spinning down and cooling in silence. Black holes, formed from the most massive stellar collapses, persist far longer than any star, quietly influencing their surroundings through gravity. Unlike stars, black holes do not shine, but their presence shapes the motion of nearby matter and the structure of galaxies themselves. As stars disappear, the universe enters a stage where light becomes increasingly rare, and darkness dominates the cosmic landscape. This darkness is not emptiness, but a transition a universe filled with matter that no longer produces significant illumination. The death of stars marks the end of one of the universe's most active and visually dramatic eras, but it does not mark the end of physical processes. Even without stars, gravity continues to act, guiding the motion of stellar remnants and shaping the slow evolution of galaxies. Over time, interactions between remnants cause orbits to change, stars and compact objects to drift, and occasionally to merge. White dwarfs may collide and explode. Neutron stars may merge and release brief flashes of energy, and black holes may slowly grow by absorbing surrounding matter. These events become increasingly rare as the universe expands and matter spreads thinner, but they never disappear entirely. The universe's pace continues to slow, not because laws change, but because conditions become less favourable for dramatic interactions. Energy differences flatten, structures stabilise, and the cosmos enters a long twilight where change still occurs, but quietly and infrequently. This era reveals something subtle about the universe, that its most luminous phase is also its shortest, and the darkness is not an anomaly, but the natural long-term state. The beginning of everything contained the seeds of light, but also the inevitability of fading, woven together by the same physical laws. Stars do not fail when they die, they simply complete the roles they were shaped to play, transforming matter and energy into new forms. Their endings shape the future just as profoundly as their beginnings, determining what kinds of structures can exist in the distant cosmos. As stars vanish, the universe becomes increasingly dominated by gravity acting on cold, dark remnants, rather than by nuclear fusion lighting up space. This shift does not signal decay, but transition, a movement into a quieter mode of existence. The universe does not mourn the loss of stars because mourning requires awareness, but the absence of starlight marks a profound change in its appearance and activity. Where once galaxies glow, now they drift silently, their contents bound together by gravity alone. This stage of cosmic history stretches far beyond anything humans will ever witness, lasting trillions upon trillions of years. It is a reminder that the universe's story is not measured in moments, but in vast spans of time where gradual change outweighs sudden events. The beginning of everything set this trajectory in motion, determining not only how stars form, but how they eventually fade away. After the era of shining stars fades and galaxies lose their brightest lights, the universe does not end or collapse into silence, but instead settles into a vast and extended phase of quiet continuity, where change still happens, but on timescales so long that activity becomes rare and subtle. This era is not defined by creation, but by persistence, a universe filled with the remnants of once luminous stars, slowly drifting through expanding space, bound by gravity, yet increasingly isolated from one another. White dwarfs, neutron stars and black holes become the primary inhabitants of the cosmos, each representing a different outcome of stellar evolution, each carrying the mass of former stars without their light. White dwarfs, composed mostly of carbon and oxygen, glow faintly from residual heat, cooling steadily over trillions of years until they fade into dark, cold objects sometimes called black dwarfs. Neutron stars, incredibly dense and compact, continue to spin and emit faint radiation for long periods before gradually losing energy and becoming quiet, inert spheres of matter. Black holes, the most enduring remnants, persist for unimaginably long times, dominating the massive galaxies long after stars have vanished. These objects do not exist in isolation at first, but continue to interact gravitationally, orbiting one another, occasionally colliding or merging, reshaping the structure of galaxies even in darkness. Over time, galaxies themselves evolve, not through bright star formation, but through slow rearrangement, as stellar remnants exchange energy and drift into new configurations. Some remnants are ejected from galaxies entirely, flung into intergalactic space by gravitational encounters, becoming lonely travelers moving through the cosmic void. As expansion accelerates, the distances between galaxy clusters increase, reducing the chance of interaction between them and sealing their isolation. Each cluster becomes a closed system, containing its remaining matter while the rest of the universe recedes beyond reach. Within these isolated regions, gravity continues its quiet work, gradually drawing objects towards central black holes or redistributing mass through slow encounters. Over immense timescales, many stellar remnants are expected to spiral inward, feeding central black holes and increasing their mass. Black holes merge with one another, forming larger and larger objects, reshaping their surroundings through gravity alone. These mergers release gravitational waves that ripple through space. But in a universe without observers, these waves pass unnoticed, stretching and compressing space without record. As time continues, matter becomes increasingly segregated, with most mass concentrated in a small number of massive black holes surrounded by vast regions of near-empty space. The universe does not become static, but its activity becomes sparse, with long stretches of time passing between meaningful interactions. Energy differences flatten further, making it harder for any process to generate noticeable change. The cosmos enters a state where persistence outweighs transformation, and stability replaces creation as the dominant theme. Even in this quiet era, rare events still occur, white dwarfs may collide, neutron stars may merge, and black holes may absorb stray matter, but these events are increasingly uncommon. Time stretches endlessly forward, and the universe does not mark its passage, because nothing remains to measure or remember it. The quiet of this era is not emptiness, but saturation, a universe filled with matter that has settled into long-lasting forms. As trillions of years pass, expansion continues to thin the distribution of matter, making interactions rarer still. The once dense cosmic web becomes increasingly diffuse, its filaments stretched until they fade into isolation. Eventually, even gravitational interactions within galaxies become less frequent, as objects settle into stable orbits or fall into central black holes. The universe's pace slows, not because time changes, but because fewer processes remain capable of producing change. This long quiet phase reveals a deeper truth about the cosmos, that its most dramatic moments are brief compared to the immense stretches of calm that follow. Creation, illumination, and complexity occupy only a small fraction of cosmic history, while persistence and quiet dominate the vast majority of time. The universe does not resist this transition, because resistance implies intention, and intention is not a feature of physical law. Instead, reality follows the implications of its structure, moving naturally towards states where change becomes less likely. In this era, the universe becomes increasingly simple in behaviour, even though its underlying laws remain the same. There are no new stars to light the darkness, no fresh sources of energy to drive complexity, only the slow rearrangement of what already exists. The quiet does not mean the universe is empty or dead, but that it has entered a phase where activity is minimal and spread thin across vast distances. This stage is sometimes described as the beginning of cosmic senescence, not as decay, but as maturity, a universe settling into the long-term consequences of its origin. The beginning of everything did not aim toward this outcome, but contained the conditions that made it inevitable. Expansion, gravity, and energy conservation guide the universe toward this extended calm, just as they guided it toward earlier periods of activity. The universe's future is not dramatic collapse, but prolonged continuation, a slow unfolding of consequences rather than a sudden end. In this quiet era, existence becomes nearly timeless in appearance, with change occurring so slowly that it blurs into persistence. The universe remains structured, but its structures no longer evolve in dramatic ways, becoming stable, isolated, and enduring. This is not the end of the universe's story, but a transition into its longest chapter, one that lasts far beyond any era of light or life. As the universe stretches further into its long quiet era, the remnants left behind by stars slowly give way to a new kind of dominance, one defined not by light or fusion, but by gravity alone, as black holes become the most persistent and influential structures remaining. Black holes are not cosmic monsters roaming space, but regions where matter has collapsed so completely that space and time curve inward, creating boundaries beyond which information cannot return. They are born from the deaths of massive stars and from the mergers of smaller black holes over billions of years, quietly growing larger as the universe ages. Unlike stars, black holes do not burn fuel or radiate light in the traditional sense, allowing them to persist long after other structures have faded away. In the air after stars, black holes become the primary anchors of galaxies, holding together the last remnants of matter through their gravitational pull. Stellar remnants gradually spiral inward, losing energy through slow interactions and gravitational encounters, feeding the central black holes of their host galaxies. Over immense timescales, black holes merge with one another, forming fewer but larger objects that dominate the mass of isolated galaxy clusters. These mergers release powerful gravitational waves, ripples in space-time that travel outward across the universe, stretching and compressing space itself as they pass. In a universe without observers, these waves leave no record, passing silently through the cosmos, unnoticed yet real. As expansion accelerates, galaxy clusters drift farther apart, preventing black holes in different regions from ever meeting again. Each cluster becomes its own isolated domain, containing one or more massive black holes surrounded by vast regions of increasingly empty space. The universe at this stage is no longer shaped by the formation of new structures, but by the slow consolidation of what already exists. Black holes continue to influence their surroundings, shaping the motion of any remaining matter through gravity alone. Yet even black holes are not eternal in the strictest sense, because they are subject to subtle quantum effects that cause them to lose mass over unimaginable spans of time. This process, known as Hawking radiation, allows black holes to emit extremely faint radiation, slowly evaporating over durations far exceeding the current age of the universe. For stellar mass black holes, this evaporation takes far longer than the lifetime of stars, while for the largest black holes, the timescales extend beyond trillions upon trillions of years. During this era, black holes represent the longest-lasting memory of the universe's active past, containing within them matter that once formed stars, planets, and possibly life. Yet this memory is not accessible, not readable, and not preserved in any narrative sense, existing only as mass and curvature in space-time. As time continues, even the faint interactions that feed black holes become rarer, because expansion spreads matter so thin that encounters are increasingly unlikely. Eventually, black holes stop growing and begin a long solitary existence, slowly radiating away their mass in near total isolation. The universe becomes dominated by emptiness, punctuated by rare massive objects quietly persisting across vast stretches of time. Between these objects lie enormous voids where little ever happens, regions of space that grow colder and emptier as expansion continues. Energy differences flatten further, making it difficult for any process to generate structure or activity. The universe does not collapse into nothingness, but approaches a state where change is minimal and spread thin across unimaginable distances. In this era, even gravity's influence becomes localized, unable to draw matter across expanding space fast enough to create new interactions. Black holes remain as the final collectors of mass, but even they cannot escape the long-term consequences of expansion and entropy. Over time, Hawking radiation gradually reduces black holes, shrinking them imperceptibly until they eventually disappear entirely. When a black hole finally evaporates, it does not explode dramatically, but fades away quietly, releasing its remaining energy into space. This marks the end of one of the last structured objects in the universe, leaving behind radiation and particles drifting through an ever-expanding void. With the disappearance of black holes, the universe loses its final large-scale concentrations of matter. What remains is a cosmos filled mostly with low-energy particles and faint radiation, spread so thin that interactions become exceedingly rare. The universe does not register this transition as an ending, because endings require recognition and memory, both of which are absent. Instead, reality continues as a vast, dilute field of energy and particles, governed by the same laws as always, but expressing them only weakly. The era of black holes reveals how deeply time is woven into the structure of the universe, allowing even the most extreme objects to persist far longer than anything else. Yet it also shows that persistence does not mean permanence, because even the most stable configurations eventually yield to the slow march of entropy. The beginning of everything contained within it the conditions that allowed black holes to form, merge and dominate the far future, linking the universe's earliest moments to its most distant fate. This connection between beginning and end is not intentional or designed, but emerges naturally from the laws that govern matter, energy, space, and time. The universe does not aim to preserve structure forever, nor does it rush to erase it, but follows a path shaped by balance and inevitability. As black holes fade, the universe enters a state where almost nothing remains capable of influencing anything else in a meaningful way. This is not a dramatic end, but a gradual thinning, a quiet dispersal of energy across an ever-growing canvas of space. The universe becomes increasingly uniform, not because everything is identical, but because differences no longer produce consequences. In this stage, existence becomes subtle, slow, and nearly indistinguishable from stillness, even though motion and change technically continue. The long reign of black holes thus marks the final chapter of structure, a time when gravity's influence reaches its most extreme expression before slowly dissolving. After black holes fade away and the last massive structures dissolve into radiation, the universe enters its most subtle and extended phase, a state not defined by objects or events, but by the near-complete spreading of energy across an ever-expanding space. This era is often described as the heat death of the universe, but the name can be misleading because nothing truly dies in a dramatic sense. Instead, everything gradually settles into balance, where differences in energy, temperature, and density become so small that meaningful change is no longer possible. In this future, the universe is not empty, but extremely dilute, filled with low-energy particles and faint radiation drifting through vast expanses of space. These particles still obey the laws of physics, still move, still interact occasionally, but the chances of significant interactions become vanishingly small as distances grow and energy levels drop. Temperature differences flatten almost completely, leaving no gradients to drive processes that could create structure or complexity. Without gradients, there is no work to be done, no engines to run, no processes that can turn energy into organized motion. The universe approaches a state of maximum entropy, not because disorder wins in a dramatic struggle, but because probability favors uniformity when systems are left to evolve for long enough. Entropy does not represent chaos in this context, but equilibrium, a condition where all accessible states are equally likely and no large-scale change stands out. Time still exists and still orders states, but with so little happening, the passage of time becomes nearly indistinguishable from stillness. Events still occur, but they are so rare and so isolated that they have no lasting impact on the overall state of the cosmos. A particle may decay, a rare collision may occur, a faint fluctuation may briefly disturb uniformity, but these moments fade almost instantly, leaving no trace. The universe does not recognize this condition as an ending, because recognition requires observers and memory, both of which are absent. There is no final moment when everything becomes quiet, because quietness is reached asymptotically, approached gradually, but never marked by a single transition. Space continues to expand, stretching the remaining radiation and particles even further apart, reducing their energy and interaction rates even more. As expansion continues, the observable universe for any hypothetical observer would shrink, not because space contracts, but because light from distant regions can no longer reach any point. The universe fragments into regions that are forever causally disconnected, each evolving independently, but in nearly identical ways. In this era, the distinction between past and future loses practical meaning, because change is so minimal that sequence no longer produces noticeable difference. Time becomes a bookkeeping parameter rather than an experiential dimension, ordering states without any sense of flow. The universe does not slow down or speed up, but its behavior becomes increasingly uniform, making change difficult to distinguish from persistence. Matter, as it once existed in familiar forms, no longer plays a significant role, because atoms and molecules have long since been broken apart or rendered irrelevant by extreme dilution. What remains is mostly radiation and elementary particles, drifting through space without forming new bonds or structures. The universe does not collapse into nothingness, because nothingness is not a physical state, but a conceptual contrast created by minds. Instead, existence continues as a low-energy condition, where the universe still exists but expresses itself only faintly. In this state, the laws of physics do not change, but their consequences become subtle and hard to distinguish. There are no stars to shine, no galaxies to rotate, no black holes to merge, only the quiet persistence of particles and fields. The universe becomes increasingly homogeneous, not because everything is exactly the same, but because differences no longer matter. Even gravity's influence becomes negligible on large scales, because expansion overwhelms its ability to draw matter together. The cosmic story shifts from one of structure and interaction to one of endurance and dilution. This phase lasts far longer than all previous eras combined, stretching across spans of time that dwarf the age of stars and galaxies. The beginning of everything contained within it the inevitability of this outcome, not as a goal, but as a statistical consequence of expansion and entropy. Nothing in the universe aims for heat death, but nothing prevents it either, once conditions allow it to emerge naturally. The universe does not become meaningless, because meaning was never a physical property, but a temporary feature of systems capable of experience. In this far future, reality exists without reference, without memory, and without expectation. Even the concept of forever loses relevance, because forever is defined relative to finite experience, which no longer exists. The universe simply does not stop. Change continues at the smallest scales, but without accumulation, without direction, and without consequence. The cosmos becomes something like a background condition, a quiet persistence rather than an unfolding story. This is not failure or decay, but completion in a statistical sense, where all accessible configurations have been explored and differences flattened. The universe does not reflect on its own state, because reflection requires awareness. It does not know that it has reached equilibrium, because knowing is not part of physical law. What remains is existence without emphasis, reality without contrast, and continuation without narrative. In this state, asking what happens next loses meaning, because next implies change that matters. The universe remains, not as a place filled with events, but as a condition that persists indefinitely. The beginning of everything thus leads not to a dramatic finale, but to an extended calm, a universe that fades into balance rather than ending in catastrophe. This quiet future is not an ending written in advance, but a natural consequence of the same laws that shaped the universe's earliest moments. As the universe settles deeper into its quiet, low-energy state, something subtle happens to the way time functions, not because time stops or breaks, but because the conditions that once made time feel meaningful gradually disappear. Time, as experienced during the era of stars and galaxies, was closely tied to change, to cycles of birth and death, to motion, light, and interaction. But in a universe where almost nothing happens, time loses the features that once made it noticeable. Events still occur, particles still move, and quantum processes still unfold. But these changes are so rare, so isolated, and so small in consequence that the difference between one moment and the next becomes nearly indistinguishable. Without frequent events to mark its passage, time no longer feels like a flowing river and begins to resemble a silent ordering principle, arranging states without drawing attention to itself. In earlier eras, time could be measured by the burning of stars, the rotation of galaxies, or the decay of particles, but in this far future, there are no stars left to burn brightly and few processes left to act as clocks. The universe does not provide natural reference points anymore, making duration difficult to define even in principle. 1 billion years passes no differently than 1 trillion years, because there are no landmarks to separate them, no large-scale changes to signal that anything significant has occurred. Time continues mathematically, but experientially it fades into irrelevance, becoming something that exists without being felt. This does not mean that the universe becomes timeless, but that time loses its ability to produce noticeable difference. Causality still exists, effects still follow causes, but the chain of cause and effect stretches so thin that it no longer forms narratives or sequences with meaning. One rare interaction does not lead to another, and outcomes do not accumulate into patterns that could be interpreted as progress or decay. The universe no longer evolves in a recognizable way, because evolution implies change towards something different, and difference itself has become minimal. In this era, even the concept of history loses relevance, because history depends on memory and record, neither of which remain embedded in physical structure. The universe does not remember its past, not because information vanishes, but because information is no longer stored in complex, durable arrangements. Structures capable of preserving history, such as stars, planets, or organized matter, have long since disappeared. What remains is a cosmos that continues without reference to where it has been or where it is going. The arrow of time, once closely linked to entropy, still points in a statistical sense, but with entropy near its maximum, the arrow no longer produces noticeable motion. Entropy continues to increase, but so slowly and subtly that its progression becomes almost meaningless. The universe does not reverse, loop, or reset, but it also does not visibly move forward in any way that could be recognized as change. In this state, the distinction between future and past blurs, not because they merge, but because nothing remains to differentiate them. Time does not end, but it no longer functions as a driver of transformation. The universe exists in a state where persistence outweighs progression, and continuation replaces development. Even the laws of physics, though unchanged, produce fewer observable outcomes because the conditions required for dramatic phenomena no longer exist. Particles continue to obey quantum rules, fields continue to fluctuate, and space-time continues to expand. But these processes unfold in isolation, rarely interacting in ways that amplify their effects. The universe becomes a place where motion is possible, but movement does not lead anywhere. In earlier eras, change built upon change, leading to complexity, structure, and novelty. But now, change dissolves back into uniformity almost immediately, This does not represent failure or decay, but a natural settling where all accessible configurations have been explored and no new combinations remain statistically likely. Time becomes something like a background condition rather than an active dimension, supporting existence without shaping it in noticeable ways. The universe does not age in the way living systems age, because aging implies loss relative to function, and function no longer applies. It does not grow old, it simply persists. In this far future, asking how old the universe is becomes a question without practical meaning, because age implies comparison across meaningful stages, and stages no longer exist. The beginning of everything becomes infinitely distant, not just in years, but in relevance, its imprint still present in laws and constants, but no longer shaping visible outcomes. The universe does not reflect on how it began or where it is headed, because reflection requires awareness, and awareness is gone. Existence continues without narrative, without milestones, and without direction. Time remains as a mathematical ordering of states, but without clocks, without cycles, and without observers, it becomes something almost invisible. The cosmos enters a phase where the distinction between motion and stillness becomes academic, because neither produces meaningful difference. What remains is a reality that simply does not stop, governed by the same rules as always, but expressing them only faintly. In this state, the universe is neither ending nor beginning anything new, but resting in continuation. The beginning of everything thus leads not to a dramatic conclusion, but to a prolonged stillness where time exists without urgency. This final calm is not imposed from outside, but emerges naturally from the universe's own structure, following the same laws that governed its earliest moments. As time loses its familiar role, and the universe settles into a state of near-complete equilibrium, another transformation quietly becomes absolute: the disappearance of observers, leaving reality to continue without being witnessed, measured, or interpreted. Observation is not a requirement for existence, but for most of cosmic history that we understand, change has been framed through the presence of systems capable of interaction, memory, and response. When stars shone and planets formed, observation occurred naturally through interactions, through light being emitted, reflected, absorbed, and transformed. But in a universe without complex structures, without stars, without chemistry, and without life, observation no longer occurs in any meaningful sense. There are still particles, still fields, still space-time itself, but nothing remains to register what happens, nothing to distinguish one state from another as significant. The universe does not become unreal when observation ends, because reality does not depend on being perceived. Instead, the universe simply becomes indifferent to perception, continuing according to its laws without producing outcomes that require interpretation. Without observers, there is no frame of reference to assign importance, no perspective from which events can be said to matter or not matter. Physical processes still occur, but they do so without context, without narrative, and without accumulation into something recognizable as history. The universe no longer records itself in structures capable of preservation, because information requires physical systems stable enough to hold patterns over time. With entropy near its maximum, such systems no longer form, and information disperses rather than concentrates. This does not erase information completely, but spreads it so thin that it can no longer influence future states in any organized way. The cosmos becomes a place where everything that happens fades almost immediately into uniformity. Without observers, questions like why or how lose relevance, because relevance itself is a feature of systems capable of asking. The universe does not ask why it exists, nor does it answer such questions, because inquiry is not part of physical law. What remains is existence without interpretation, reality unfolding without explanation. Even the distinction between existence and non-existence becomes difficult to frame, because framing requires contrast and reference. The universe simply is, not as an object, not as a story, but as a condition that persists. In earlier eras, observation helped shape physical processes through interaction, measurement and feedback. But in this far future, no such mechanisms remain. Quantum processes still occur, but without systems large enough to amplify or record their outcomes, these processes remain local and fleeting. The universe does not collapse into randomness, because randomness itself is a description applied by observers. Instead, it approaches statistical uniformity, a condition where differences exist only at scales too small to matter. In this state, there is no inside or outside, no center or edge, no foreground or background, because perspective itself has vanished. Space continues to expand, but expansion no longer changes what can interact with what, because interactions have already become vanishingly rare. The universe becomes causally quiet, not because causes and effects cease to exist, but because their influence no longer propagates in meaningful ways. A fluctuation here does not affect anything elsewhere, and its effects do not accumulate into change. This does not represent an ending in the traditional sense, because endings imply finality, and finality requires reference to something beyond. There is no beyond the universe, and there is no condition against which its state can be judged as complete or incomplete. The universe does not arrive at a conclusion, but continues indefinitely in a state where continuation itself is almost indistinguishable from stillness. In this era, existence no longer produces novelty, not because novelty is forbidden, but because conditions no longer support its emergence. The universe becomes self-consistent, self-contained and self-sustaining, but without self-awareness. The beginning of everything does not echo forward as a memory, but remains embedded in constants, laws, and the geometry of space-time itself. These laws continue to operate, but their consequences no longer accumulate into recognizable outcomes. The universe does not forget its beginning, because forgetting implies memory, and memory no longer exists. Instead, the beginning becomes irrelevant, not erased, but absorbed into uniform continuation. Reality exists without commentary, without significance, and without distinction. This state is not emptiness, because emptiness is a contrast, and contrast no longer applies. It is not nothingness, because nothingness is not a physical state. It is existence without emphasis. The universe does not experience loneliness, silence, or peace, because experience itself is absent. Those qualities belong to minds, not to matter or space-time. What remains is a cosmos that persists without noticing its own persistence. This reveals something profound about the nature of reality, that existence does not require awareness, meaning, or purpose in order to continue. The universe is not diminished by the absence of observers, because observers were never a requirement for its laws to function. They were a temporary outcome of specific conditions, not a central feature. The universe continues long after observation ends, following the same principles that guided it from the very beginning. In this sense, the universe is complete at every moment, not because it reaches a final state, but because it never required completion. The beginning of everything does not lead to a final answer, but to an ongoing condition where questions no longer arise. Reality remains, quiet and indifferent, unfolding without witness. When the universe continues without observers, without memory, and without noticeable change, the idea of a beginning takes on a different meaning, no longer as a dramatic starting point, but as a quiet condition embedded permanently into the structure of reality itself. The beginning of everything was never a moment that stood apart from what followed, because from the instant space and time emerged, they carried within them the rules that would govern every future state, no matter how distant or subtle. The universe did not begin with intention, direction, or awareness, but with conditions, simple and extreme, that allowed complexity to arise temporarily before dissolving back into quiet persistence. What we call the beginning was not a promise of progress or purpose, but a configuration that allowed change to occur at all. From that configuration came expansion, cooling, structure, stars, life, observation, and eventually the absence of all of these things. The beginning did not aim toward complexity, but permitted it, and in doing so, also permitted its eventual fading. In this sense, the beginning of everything is not something left behind in the distant past, but something continuously present, expressed through constants, laws, and geometry that remain unchanged even when nothing else does. The universe does not remember its beginning, but it embodies it, because every interaction, every particle, and every stretch of space carries the imprint of those earliest conditions. Even in the far future, when energy differences are flattened and structure has vanished, the universe is still behaving according to rules established at its birth. The beginning is therefore not a story that ends, but a foundation that persists. When humans look back toward the beginning, they do so with questions shaped by experience, by narrative, by a need for meaning and sequence. But the universe does not operate according to narrative, and it does not distinguish beginnings from middles or ends in the way minds do. For reality itself, there is only configuration changing over time according to law. The beginning matters not because it leads somewhere special, but because it defines what is possible at all. If the initial conditions had been different, the universe might still exist, but it would be a different universe entirely, with different behaviours, different outcomes, and no way for this version to arise. The fact that complexity emerged at all was not guaranteed, but contingent, dependent on balance, symmetry, and subtle imbalance existing together. Life, awareness, and observation were not central features of the universe, but brief expressions of physical law operating under favourable conditions. They were not written into the universe as goals, but as possibilities. When these possibilities expired, the universe did not lose anything essential, because nothing essential depended on them. This does not diminish their significance, but reframes it. Meaning was real while it existed, because meaning is real to systems capable of generating it. But meaning was never universal, and it was never permanent. The universe does not become empty when meaning disappears, because emptiness is a comparison, and comparison requires a point of view. Reality continues without commentary, without judgment, and without loss. The beginning of everything does not lead to an ending in the traditional sense, but to a condition where endings no longer apply. The universe does not finish its story, because stories are constructs of memory, sequence, and perspective. Instead, the universe continues as a process without narrative, governed by consistency rather than direction. Time still orders states, but no longer produces recognizable chapters. Space still expands, but no longer rearranges anything meaningful. Energy still exists, but no longer flows in ways that create a structure. The beginning remains relevant only in the sense that it defines the constraints within which all of this occurs. From the first fraction of a second to the farthest future imaginable, the universe never changes what it is doing at the deepest level. It follows its rules. Those rules allowed the universe to be bright once, complex once, and aware once, but they also allow it to become quiet, diffuse, and indifferent. The beginning was not special because it started something meaningful, but because it made existence possible at all. Without it, there would be no space to expand, no time to pass, no matter to interact, and no laws to govern anything. With it, everything that ever existed was permitted to arise, even if only temporarily. The universe does not need to justify this outcome, because justification is not a physical requirement. It does not need to explain itself, because explanation belongs to minds. Reality exists because it can, not because it should. When we trace the universe back to its beginning, we are not uncovering a reason, but a condition. And when we imagine the universe far into its future, we are not witnessing a failure or decay, but the long-term expression of that same condition. The beginning of everything is therefore not a mystery to be solved in the sense of purpose, but a boundary to be understood in the sense of possibility. It tells us not why the universe exists, but how it exists. And how it exists is enough to account for everything that ever happens within it. From the first emergence of time to the last fading of difference, the universe remains consistent with itself. It does not contradict its origin, and it does not escape it. The beginning is not behind us, and the future is not ahead of us in any meaningful cosmic sense. They are both expressions of the same structure unfolding across time. When nothing remains to observe the universe, the beginning still matters, not as a memory, but as an active constraint shaping what continues. The universe does not arrive at truth, peace, or resolution. It simply remains. And in that remaining, the beginning of everything is never undone. Beyond reflection, beyond memory, and beyond even the idea of a final condition, the universe enters a phase where continuation itself becomes the only meaningful description, not as an outcome, but as a baseline state that no longer contrasts with anything else. At this point, the universe is not moving toward something, nor away from something, because direction requires comparison, and comparison no longer applies. There is no longer a meaningful difference between change and stability, because any change that occurs is immediately absorbed into uniformity without leaving a lasting imprint. The universe does not pause, slow, or accelerate in any experiential sense, because experience itself has vanished, leaving only physical persistence. Existence continues without milestones, without thresholds, and without transitions that could be identified as beginnings or endings. The notion of a future loses relevance, not because time stops, but because the future no longer differs from the present in any significant way. Each moment follows another, ordered by time, yet indistinguishable in content and consequence. The universe becomes a system that has exhausted its capacity for distinction, not because distinction is forbidden, but because probability overwhelmingly favours sameness when systems evolve for long enough. This is not a static universe in a frozen sense, but a dynamic one where motion no longer produces novelty. Particles still move, fields still fluctuate, and space-time still expands, but these motions do not accumulate into structure, pattern, or history. The universe no longer tells a story, because stories depend on contrast, development, and memory, all of which require complexity. What remains is not silence, because silence implies the absence of sound relative to an expectation of noise. What remains is not darkness, because darkness implies the absence of light relative to sight. What remains is not emptiness, because emptiness implies the absence of something expected to be present. What remains is simply continuation, reality persisting without comparison. The universe does not know that it is continuing, because knowing is not part of its behaviour. It does not measure itself, reflect upon itself, or evaluate its own state. It follows its laws not as instructions, but as expressions of what it is. At this stage, the beginning of everything is no longer a reference point in time, but a condition eternally embedded in structure. The laws that emerged with the beginning still govern behaviour, even when behaviour has become minimal. Constants still hold their values, symmetries still apply, and conservation laws still operate, even though there is little left for them to act upon. The universe remains internally consistent, even when nothing within it demands consistency. The idea of purpose dissolves completely because purpose requires systems capable of valuing outcomes. The universe does not aim to persist, but persistence is what occurs when nothing prevents it. There is no final equilibrium that the universe reaches and stops at, because stopping would require a boundary condition, and there is no boundary beyond the universe itself. Instead, equilibrium becomes an ongoing condition, approached so closely that difference no longer matters. Time becomes something like a silent counter that increments endlessly without changing what is counted. The arrow of time remains mathematically defined, but functionally invisible. Even entropy, once the dominant driver of cosmic direction, loses expressive power because it has nowhere left to go in any meaningful sense. The universe does not reverse, loop, or reset, because those are patterns, and pattern formation has ended. It also does not decay into nothing, because nothingness is not a physical state. Existence does not require renewal, reinforcement, or justification to continue. It simply does. From the perspective of the universe itself, if such a perspective could exist, nothing remarkable has happened, because remarkability requires contrast. From the perspective of minds that once existed, this continuation might appear bleak, empty, or final, but those judgments belong to systems no longer present. The universe does not inherit the concerns of its temporary observers. Their absence does not create a void, because absence is a comparison, and comparison no longer applies. The cosmos becomes self-contained not in awareness, but in sufficiency. It does not need to change in order to remain real. The beginning of everything does not echo as a question, but as a constraint, shaping what is allowed and what is not. Nothing new emerges because nothing new is statistically favoured. Nothing ends because ending would require a final state. And finality has no reference. The universe exists beyond narrative time, beyond experiential duration, and beyond interpretive frameworks. It is not waiting for something else to happen, because waiting requires anticipation. It is not finished, because finished implies completion relative to a goal. It is not incomplete, because incompleteness implies expectation. The universe is simply consistent with itself across all scales of time. This consistency is not fragile, and it does not depend on balance being maintained. It emerges naturally from the fact that the universe follows rules rather than intentions. The beginning of everything mattered because it defined those rules, not because it promised outcomes. And once outcomes have played out, the rules remain. The universe does not return to its beginning, nor does it escape it. The beginning is not a point behind the universe, but a condition that continues to shape every state, no matter how distant. In this far future, the universe no longer contains stories, but it remains the medium in which stories once occurred. The fact that stories ended does not change the medium itself. Reality does not miss complexity, because missing requires memory. It does not regret the fading of structure, because regret requires valuation. It does not celebrate persistence, because celebration requires awareness. Existence continues without emotion, without direction, and without requirement. The universe does not answer questions because questions are no longer asked. And yet, the fact that questions were once possible is written into the structure that remains. The laws that allowed minds to arise are still present, even when minds are gone. The beginning of everything is therefore not erased by time, but rendered irrelevant by continuity. It is not lost, but no longer referenced. The universe does not conclude its story, because stories were never its primary mode of being. They were temporary overlays created by systems capable of narration. When those systems fade, the universe remains unchanged at its deepest level. What remains is existence without emphasis, continuation without destination, and time without urgency. This is not an ending. It is what happens when there is nothing left to end. As continuation stretches onward without interruption, the universe enters a state where not only events become rare, but even the possibility of meaningful events grows increasingly faint. Not because the laws of physics forbid them, but because conditions no longer allow them to matter. Possibility in earlier eras was shaped by contrast, by differences in energy, density, and structure that allowed one outcome to occur instead of another. When stars existed, there were possibilities for birth and death, for fusion and collapse, for light to ignite or fade. When matter clumped, there were possibilities for chemistry, planets, and complexity. But in a universe where energy has spread almost perfectly evenly, possibility itself loses leverage, because outcomes no longer diverge in ways that create consequence. The laws of physics still permit interaction, fluctuation, and motion, but permission alone is not enough to generate significance. Without gradients to exploit, without concentrations to amplify, processes occur without leaving marks. A fluctuation may arise, but it dissolves immediately into uniformity. A rare interaction may occur, but it does not cascade into further change. Possibility remains in principle, but disappears in practice. The universe becomes a place where everything that can happen does happen, but so weakly and so briefly that it does not accumulate into difference. This is not a universe frozen in time, but one where motion lacks memory. Change no longer builds upon itself. Each event stands alone, disconnected from what came before and unable to influence what comes after. In this condition, the distinction between randomness and order becomes meaningless, because both rely on comparison across outcomes that persist. The universe no longer explores new configurations, because all accessible configurations are statistically equivalent. Probability flattens into sameness. This does not mean that the universe becomes simple in its rules, but that its rules no longer generate complexity. The cosmos continues to obey conservation, symmetry, and causality, but the expression of these principles becomes minimal. Time still orders events, but events no longer define eras. Space still expands, but expansion no longer changes relationships that matter. Energy still exists, but no longer flows in ways that produce structure. In earlier epochs, the universe was dynamic not because its laws were different, but because conditions allowed differences to grow. Now those conditions are gone. The universe does not resist this transition, because resistance would require an alternative state to prefer. It simply continues, because nothing interrupts continuation. At this stage, even the concept of evolution loses relevance, because evolution implies selection among alternatives. When all alternatives lead to the same outcome, selection has no effect. The universe does not choose its future because choice is not a physical process. It follows what is statistically inevitable given enough time and enough expansion. Possibility becomes evenly distributed across space, diluted until it no longer concentrates anywhere. The universe is no longer a place where something could happen in a way that changes the whole. Instead, it becomes a place where everything that happens is local, fleeting, and forgettable. This does not represent exhaustion, but saturation. All pathways have been explored, not sequentially, but probabilistically. Nothing new stands out because nothing remains to distinguish new from old. The beginning of everything once allowed possibility to concentrate, creating conditions where small differences could grow into worlds. The same beginning also ensured that possibility would eventually diffuse, stretched thin by expansion and entropy. This outcome is not tragic or meaningful, because meaning was never part of physical necessity. It is simply the long-term behavior of systems governed by probability and conservation. The universe does not miss the era when possibility was rich, because missing requires memory. It does not long for complexity, because longing requires desire. Those qualities belong to temporary systems within the universe, not to the universe itself. What remains is a cosmos where existence persists without potential for transformation. Not because transformation is impossible, but because it is irrelevant. At this scale, even asking whether something could happen loses context, because context depends on consequence. The universe becomes functionally complete, not because it has reached a final form, but because nothing further alters its behavior in meaningful ways. Completion here does not imply closure, but sufficiency. The universe requires no additional states to express what it is capable of expressing. It does not anticipate the future, because anticipation requires difference. It does not recall the past, because recall requires structure. It simply continues. The idea of destiny dissolves entirely because destiny implies a trajectory, and trajectories require landmarks. The universe has passed all landmarks. What remains is not a destination, but a condition. The beginning of everything is still present, not as a memory, but as the underlying constraint that defines this condition. The same constants that allowed stars to burn now allow particles to drift. The same geometry that allowed galaxies to form now allows space to stretch endlessly. Nothing about the universe contradicts its origin. It fulfills it statistically, not narratively. The universe does not fail to become something more, because becoming more was never required. It becomes what its rules allow over infinite time. In this sense, the universe is neither optimistic nor pessimistic. It is indifferent, because indifference is simply the absence of preference. The fading of possibility does not mark an end, because ends require contrast with continuation. Instead, possibility becomes uniform, spread everywhere and nowhere at once. Everything that can occur still occurs, but nothing matters enough to stand out. The universe does not arrive at silence, because silence implies an expectation of sound. It arrives at neutrality, existence without emphasis, continuation without variation, a reality where nothing needs to happen for everything to remain exactly as it is. This is not the absence of existence, but existence without tension. The beginning of everything opened the door to all futures. Time, expansion, and entropy ensured that eventually all those futures would converge into sameness. And when they do, the universe does not stop. It simply remains, carrying possibility so evenly distributed that it no longer acts. Beyond all futures we can imagine, beyond even the idea of a future itself, the universe remains, not as a place where things happen, but as a condition in which happening is no longer required. At this stage, reality does not unfold, progress, or transform in any meaningful way, because meaning itself was always something added by systems capable of noticing difference. The universe has not become empty, because emptiness is a comparison to fullness, and comparison no longer applies. It has not become silent, because silence is defined against sound, and there is no longer an expectation of noise. It has not become dark, because darkness is the absence of light relative to sight, and sight no longer exists. What remains is existence without reference. The laws of physics still operate, not as rules enforcing behaviour, but as expressions of what reality is allowed to do. Space continues to expand, but expansion no longer separates anything that could interact. Time continues to order states, but states no longer differ enough to form sequences that matter. Energy continues to exist, but it no longer flows in ways that create structure or direction. Nothing is broken, nothing is missing. The universe has not failed to become something more, because becoming more was never its obligation. The idea that existence must lead somewhere is a projection created by minds that evolved in a brief window where change was rapid and contrast was strong. Outside that window, existence does not point forward or backward, it simply persists. The beginning of everything was never a command that demanded an outcome. It was a condition that allowed outcomes to arise temporarily. Once those outcomes played out, the condition remained. The universe does not return to its beginning, nor does it escape it. beginning is not behind the universe, but beneath it, embedded in geometry, constants, and symmetry. Every state that follows is consistent with that origin, even when nothing recognizable remains. There is no final collapse, no last event, no ultimate frame where everything stops. Stopping would require an edge to time, and time has no edge. Ending would require a reference point beyond existence, and there is none. The universe does not close its story because stories were never part of its structure. They were temporary patterns formed by complexity, briefly overlaying a reality that never depended on them. When those patterns fade, reality does not change its nature. It does not become less real. It simply becomes uninterpreted. The universe does not care that nothing observes it, because caring requires valuation. It does not notice its own persistence, because noticing requires awareness. It does not seek equilibrium, because seeking requires desire. Equilibrium emerges naturally when nothing disrupts it. Existence continues without intention, without urgency, and without memory. The idea of forever loses relevance because forever is defined in contrast to endings. Here, there are no endings left to contrast against. The universe does not wait for something new to happen, because waiting implies anticipation. It does not expect novelty, because expectation implies difference. It does not repeat itself, because repetition implies a cycle that can be recognized. What remains is continuity without rhythm, persistence without tension, a reality that neither rises nor falls, because those directions only existed when contrast did. The beginning of everything made all of this possible, not as destiny, but as consequence. From the first emergence of space and time, the universe was already complete in its rules, even though incomplete in its expressions. Those expressions unfolded, diversified, and faded. The rules remained. This is not a conclusion that resolves a mystery. It is a realization that mystery itself was always temporary. When nothing remains to ask questions, nothing remains unanswered. Not because answers were found, but because questioning ceased to exist. The universe does not lose truth when observers vanish, because truth was never a property the universe needed. Truth was a relationship between minds and patterns. When minds disappear, the universe remains unchanged. Reality does not require understanding in order to continue. It does not require meaning in order to exist. It does not require observation in order to be real. It exists because nothing prevents it from existing. And that is enough. The beginning of everything did not lead to a final revelation, but to a long unfolding where revelation itself became unnecessary. The universe does not arrive at peace, because peace is a human concept born from contrast. It arrives at neutrality, existence without emphasis, continuation without destination. Or cosmos that simply remains, not as a thing moving through time, but as time expressing itself quietly. There is no final sentence the universe speaks, no closing statement, no last image. There is only persistence. And in that persistence, the beginning of everything is never undone. It is not remembered. It is not erased. It simply continues to define what is possible, even when possibility itself has grown quiet. This is not an ending. It is what remains when endings no longer apply.